My name is Bill Porto. I work with Redpoint Global, and this is going to be my take on machine learning and different aspects and how it might affect your guys' lives. First of all, I'd like to thank the organizers and especially the volunteers for putting on this conference. I think they're doing a fantastic job. I've been involved in a number of different IEEE conferences, and I think we all give them a round of applause for the job that they're doing right now. It would be nice. Second, I'd like to thank my employer for letting the squirrel out of the cage today so they could talk here. They even gave me this nifty gray shirt so I can blend in at night and dark when the power goes out in San Jose. And third, I'd like to also thank all the people who submitted abstracts here that did not get accepted. It's only because they got a few less votes that I'm here today as well. Okay, see if this thing works. All right, so if there are three basic things I'd like you to take home today, and if you get anything, just try to remember these three things. Machine learning is all about prediction, trying to figure out what you want to do with the future, how you're going to do it. Optimization, how you can optimize things and keep current. And finally, automation and adaptation. And that's really the key to this whole talk. See if I can get this thing going. This is the death knell for business. Now I'm going to put a little bit of marketing-centric approach on this, specifically because, well, they're paying me to do this, and this is part of my job. But it applies to just about every type of field that's out there and every type of business as well. It doesn't matter whether you're a PhD student and you're trying to sell your idea to your thesis advisor, or if you're a politico trying to sell your message to people. It all is marketing, sales of some ideas to various people. Kettering probably said it best here. If you're not moving forward, if you're doing the same thing, you're probably doing something wrong. And it is so true. Stasis is something that we're all used to over here. People like keeping things static. It's comfortable. It's just something we're used to doing. Problem is the world changes, and that's not something that really mixes very well. The typical problem that you see is, like for maybe segmentation, is people will say, okay, I've got 5 different focus groups. Okay, I've got the 18 to 25s, preteens, the 25 to 40s, the 40 to 60s, and then after that, the dinosaurs. We don't care about that. Well, that doesn't work anymore. The dinosaurs now actually have a lot of money. They're spending it. Those can be segmented in different ways as well. And you need to take advantage of that information and look at it in a lot of different ways. Hadoop is a fantastic technology, and it's allowing people to access, to store, and to process data in a lot of different ways that were not available 10, 15 years ago. It allows us to do many different things, many different ways, and a lot faster than what we do. And especially is very well suited to some of these machine learning tasks as well. One thing you've also got to remember is that because of change, because of stasis, we will see changes as well in Hadoop and also in the different processing technologies. I would guess that in 10 years, maybe not to the like of this conference, we'll probably see a different technology come up. I don't know what you're going to call it, Panda, we'll have a new mascot, Ling Ling, who knows. But there will be a new technology come up to replace this. It just gets better and better. The thing here is change and adaptation to that change, and that's the key to success. Okay, so from the start here, some of the basic definitions, and again, this is my take on what I think learning is, and there may be other people out here who think a little differently, so take it with a grain of salt, but I think there's some basic tenets here that apply to all things. One of the first things is the difference between learning and instruction. Instruction is pretty much static rules. So you set down a set of rules, you're going to tie your shoelaces. You learn that once, you pretty much don't change for the rest of your life on how you do that. Maybe you gain a little weight, you can't see your shoes, so you have to adapt a little bit. But that's just the way it goes. Learning, on the other hand, involves memory, it involves adaptation, it involves changing the way you do things and adapting to that environment, because that's what happens. Intelligent systems are literally this. For anything really, in my view, to be intelligent, you have to have memory, something to store what you have learned, how you've learned it, and why you've learned it. You must be able to also predict, and that's what humans do very well. In fact, we're probably one of the premier species out there that does well with prediction. Computers, maybe not so much. We're training them with a lot of different algorithms as well, and they're getting better and better every day, from pattern recognition to signal processing algorithms to everything else. But again, humans learn instinctively, and even though we have billions of cells in our heads, we operate on a millisecond level. That's awful, awful slow. And computers today, thank goodness, can do that on a picosecond level. Nanoseconds, that's history at this point. We're talking billions and billions of operations per second now. Another key here is assess what you're doing. So not only predict, but use that prediction, take an action, and then actually assess how well you did. Once you can assess how well you did, then you can use that and feed back into your system to figure out what you should do the next time. How are you going to change things? How are you going to change the model? How are you going to change your behavior to actually accomplish what you need to? And that accomplishment is probably going to be like survival, or to come up with a better product, or to sell something in a marketplace. So those are my takes on it. And if you think about it, the old, Lewis Carroll's Alice in Wonderland, the Red Queen, where you have to change just to keep up. If you do not change and do not keep that in light, you will not keep up. You'll lose and you'll fall behind. Okay, Niels Bohr, this is around the turn of the century, that is around 1900s, that is. Put this very succinctly, and he's a very bright man. You don't win the Nobel Prize for nothing. This is an extremely difficult task with prediction. There are a lot of things to do out there, a lot of data, a lot of things to read into it, a lot of misreading things that you can do. So I make a personal distinction between regression learning and prediction learning. And the reason here is that prediction is different. It's quantitatively different. Regression is all about the past. What did history do? Okay, that's nice. You can figure out what happened. You can draw lines. You can draw plots. You can do lots of different things with that. You can find out what's going on. The problem is that it's just that. It's just history. And granted, those who don't pay attention to history are doomed to repeat its failures, but you need to actually act on it. That's what prediction is about. Prediction is using those models to actually do something valuable with it to make your life better, to make your sales better, to get a better presentation, whatever it happens to be. That's the feedback cycle there. Recently at one of the conferences, I was asked to participate in a webinar, and I listened to this person talk about their software product, and it was a modeling tool. And I thought, okay, cool, let's see what they have. So they talked about it, and it went through a lot of different steps, and it showed, data comes in, goes to the cloud, run the model, chunks out, fine, ding, here's your model. At the end of the day, they showed a bunch of plots. You could plot just about anything you want, lines, bars and whiskers, you name it. Great. Problem is, they had not thought about how to actually use this model. So this was a great tool for putting together a PowerPoint presentation for your boss, but what good does that use to help you if you can't use it? They hadn't thought about actually writing code from that model that you can use in any sort of environment to use to predict for your task at hand. And that to me was a major oversight. So keep that in mind as well. So, a couple different ways you can break down machine learning in terms of prediction and learning itself. I'd like to think about these in terms of supervised learning and unsupervised learning. And in the supervised learning, basically you're looking at some sort of historical data where you have some sort of a known outcome, something that you can correlate with that outcome. So you took an action and then you see some sort of correlated truth that you assume was either correlated or hopefully causal. In an unsupervised method, you don't necessarily have that. You might, but you may not trust it. And that's one of the keys there as well. There are a lot of different ways. Clustering is typically done as an unsupervised model, and you can actually use the truth if you had it and you trusted it in an unsupervised model to make it better. But again, it's the problem between causation and correlation and attribution. And again, I'm going to make a little allegory here from another conference. This was a Gartner conference in San Diego that I participated in about a year ago. And it was very curious to me because most of these conferences, they have all the different people out there, vendors and people talking, and they had these little round session tables, and people were talking about different success stories they had for their software. So, fine, let's just sit there and see what's going on. So this particular company, and I won't name it, had been putting their software in as a web service for a replacement as a call center for a cable company. Now, everyone hates the cable companies. Okay, that's fine. We all agree about that. But what they did is, instead of having a call service that took them a lot of time, effort, and money, they changed everything to this nicely web-centered service. And they were showing all these graphs and plots, and they said, this is how well it's doing. Look at how much better it's doing over the amount of cost and amount of service calls that they had to actually answer. And one of the things that they showed on their particular chart was the fact that during a service outage, that the cable went out, they actually had fewer calls. Okay, so people went in that service less. All right, and fine and dandy. So at the end of this, they said, any questions? Well, being slightly politically incorrect and totally insensitive, I said, okay, one problem here. Did anyone start to think that, hey, maybe the reason why you're getting less calls is because your service was down and people could not contact the company? So they had attributed their success to the fact that they had fewer calls, and actually it was their failure that caused them to have fewer calls. So this is where you can get a mistrust of the data and the associated correlations or causations that you think might be happening. And this might actually play a role into your choice of a supervised versus an unsupervised model. Okay, so from there, this may be above, below, I don't know exactly where the audience is level in terms of machine learning technology and some of the other technological things that are going on here. In a supervised learning model, let's see if I can get this actual pointer to go here. You get basic training coming in, and you have whatever learning algorithm you have, many different types of them out there, many different types of models, no matter what. And this is where the truth comes in. This is where you actually have the labels themselves. This is what you know from what past experience that you had is associated with the outcomes that you put in particular data, okay? So you train the model goes around and around, comes out to some success criteria, and you stop it at some point. You run out of time, it comes up to some sort of error criterion. Yes, it's low enough error, or you just are impatient, you want to use the blasted thing. At that point, you have a trained model. So at that point, you can take that model, you can add new data, and just use it as straight prediction. So you pop in something, it's again, apples to apples. You can't use something that didn't get trained on in the first place in terms of like different rows and columns and types of things like that. You actually use new data, and you pop that in, and it actually comes up with outcome, and then you get the expected labels. What you thought was going to happen, that's what you actually predict. So this is the supervised paradigm. Unsupervised learning is very similar. I'll call this clustering, segmentation. They're all the same thing in terms of that. It's just basically you want to break things into smaller pieces that are recognizable by their characteristics. So take in raw data, and you do some sort of a cluster model, many of them out there. You train the model on that. You let it learn from whatever things it can actually figure out what the underlying principles are going on. You validate that. You take a look at it and say, does this make sense? If it makes sense, then maybe let's use it. If it doesn't, let's reiterate it, and you take the cluster labels and you then retune it. Sometimes that works, sometimes it doesn't. It's an iterative process. So both supervised learning and unsupervised learning are iteration processes. It's not a one shot for all. You have to actually do a little bit of work on this one. You can automate quite a few different steps, but that's pretty much what it comes down to. Again, after you've actually made the clustering model or segmentation model, you can pop in new data and then come out with whatever label it is. So if the model says, there should be 5 different clusters, it'll pop whatever data that you have into one of those 5 clusters and say, this is where it is. And then you can use that, and you can say, okay, well, let's market to these people, or let's send this information to that people, or utilize these people for a medical survey or whatever you happen to have. Okay, so a lot of different types of models out there, and I'll first talk about some of these that are supervised learning models. Linear models have been around for a long, long time. They've been around from probably the time of Gauss and Newton. This is back in the 1800s. So one of the reasons is that the math is very, very easy to do. Essentially what they are least squares, and that's something that people have had for a long, long time. And they run very quickly after they've been trained. So the idea here is you take a bunch of data, might be, X's and O's, whatever it happens to be, and height and age in this particular example, and you try to then fit a line through that. That's great if a line fits through that. Typically what happens is that you have noise on data. No data is perfect, and if your data ever is perfect, you really should suspect it as being problematic or check it further, okay? So what happens is that after you fit the line, or if you want to change the data to maybe a log transform, if it has a slight curve like that, you might be able to get by with some things like that as well. And then you can use that line then to predict what's going on in the future. Okay, if you happen to come down in this particular age, you can figure out what the height happens to be. Problem is, the world isn't anywhere near close to linear. I really honestly do not know of any purely linear process that's out there. And I've done a lot of different things. I've worked for government agencies, I've worked in the healthcare field, I've worked in pharmaceuticals. The world's just not linear. There are so many other things, so many underlying trends going on there. So what people can do is they can make this piecewise linear. Okay, that's an approximation, but again, that's just one approximation. The biggest problem here with linear models is that it treats all errors equally. Okay, and that is a really big thing that causes problems. It causes the fact that you can get not only misleading results, but ways that actually lead you in the wrong direction. If, for example, I treat all errors equally, here's a case and example. I predict the weather, okay? And tomorrow I'm going to predict rain. It happens to be sunshine. So you get a little upset. No big deal. You carried around your umbrella or maybe cancel a couple plans. It's not a big deal. But instead of that, what happens if I predict sunshine and it's actually a thunderstorm or hurricane? Big difference in the errors. There's a difference between a missed opportunity and a lost sale. Linear models, anything that has least squares techniques in it, does not account for that. They treat all the errors equally, and that is a problem with these particular techniques. They still are useful. You might want to throw them in the mix, but it's something to watch out for. Okay, another possible model here is a decision tree. And we've all seen these. Every time you go, again, you call up the cable company and say, why is my modem not working? They go down this checklist and they've got it, okay, well, is it turned on, is it turned off? Fine, okay, it's turned on. Now is the red light blinking or is the green light blinking? All of these basically are different decision tree things. It's essentially a set of if, then, else rules, typically static. Typically they do not get changed, and because of that, they're not really learning. They're not learning or adapted on the fly. That's a problem. The good thing is that they don't assume any linearity, and also you can use things that are non-numeric. You can use alphanumeric things if you'd like to. So you can say, if the person's name is Christopher and he has an income of this range, you can take that particular action on it. Okay, they use a lot of these in medical healthcare and diagnosis, and probably the next time you go to the doctor, that's one of the things that they're going to be doing. At least the nurse practitioners now rely on this quite a bit. One of the problems with these particular techniques, though, is if the trees themselves are not balanced. In this particular case, you've got two different layers of this, and each side is pretty much the same. If they become unbalanced, you have a problem because it biases results, and that's not a good thing. You can get very, very misleading results out of that as well. The other thing is that some concepts require very large trees, and we can get, at least in the healthcare industry, trees that are thousands of different nodes long, and that's a large set. If you're doing this on a computer, it's automated, not a big thing. If you're in a call center, that is a big thing because then you have to flip through lots of different pages. Think about that in terms of that, okay? There we go. Okay, so the next possibility is some nonlinear methods. Now these are actually very, very nice in that because they're nonlinear, they allow you to subsume not only linear things, but also the real world, which is typically not linear. Okay? One of the particular paradigms over here that I'm showing here is an artificial neural network. They're based on biology. Biology's been doing things for a long time. We tried to simulate what's going on in the human brain. And again, this is just a simulation. It's nowhere near what's going on. We have a lot more complexity in our brains, I hope, than these simplistic drawings. The good thing is that they're very nice in terms of universal modeling. They can model just about anything. How to do that is the challenge, but they can theoretically model just about anything. They operate very, very quickly too. The processing nodes in each one of these is just essentially a sum of some numbers and putting it through a simple function. Okay? It executes very quickly. And you don't have to assume linearity at all because of all of these transforms inside, they could be linear or nonlinear, but the sum of them also allows you to do nonlinear types of modeling. In fact, if you take the middle layer out of this thing here, this particular one, and you just use linear functions in here, guess what you get? A linear model. So you can subsume two things in one and kill two birds with one stone. Okay? Biggest problem with this is that there are a tremendous number of different techniques to do this, tremendous number of parameters to adjust, and people think of this as black magic. Okay? It's a black box, and people mistrust this because it's a black box. It's hard to decouple what they actually learn and what's in each individual node. You know, what is this particular node telling you about the data? Well, that's not an easy thing to decouple. So if you try to explain this, even if it works well, even if it's one of the best things that you can actually throw at a problem and model, and you can show to your boss, hey, look, this predicts the world very well. I get great results out of that. And your boss might come up and say, I don't trust it. How do you know it's working? Okay, and that is a problem, and it's hard to overcome at times. But this, the networks and these Bayesian networks, other types like this, they're what they call stochastic models. They use randomness in them, and the randomness allows them actually to search the space of different options and actually come up with a better solution for you in a nonlinear space. Okay, so we discussed a few different supervised learning methods. Now let's look at clustering or segmentation. I'll use those interchangeably. So here's a big question for you. Here's some raw data, a bunch of little black dots on there. How many clusters do you see? Lots. Many? A few? Who knows? This is the biggest challenge with clustering, and you don't necessarily know a priori about this. That's what you're trying to do with whatever clustering model that you have to figure out what's going on within that model. Okay? So what kinds of clustering models are there out there, and how can they actually be used? Okay, so one of the first things that you can actually do is what they call collaborative filtering. This is a very oft-used model, and it had a lot of popularity around there, and it's still being used quite often. This is what they call the wisdom of the masses. You might accept that or may not, I don't know, but it's a common denominator approach. In a sense, what you're doing is you create a matrix, and that matrix is saying, okay, well, these people bought these things in these quantities. You can use price, you can use the number of things, any cardinality, anything you like. And then you just basically look up and down and say, well, these things are similar because this guy also bought that same thing, or they did that same action. Okay? That's good and bad. The great thing is that it's nice and general. You can show lots of general things, and it's not too hard to construct these types of matrices. The bad part is that it's not personal at all. Case in point, about 2 years ago, we got a new puppy. Okay? And anybody who's had a new puppy recently knows that the first thing they do is they tear apart your house. Okay? They run around, they chew anything that they can see in sight. So the first thing we did, okay, fine, let's go to Amazon and get a couple baby gates. Solve the problem. And sure enough, that did solve the problem. It also created another big problem. Amazon uses this type of technique, collaborative filtering, to suggest to you as a product recommender what's going to happen next. Okay, I have a puppy, bought baby gates. The next day I get ads for baby formula. I get ads for diapers. It gets worse. I get an ad for breast milk pump. Now, I love my dog, but let's have a little bit of sense here, okay? This continued for a long time, so I kept on trying to figure out ways to solve this in terms of, clearing my cache, going shopping on Amazon for different types of products. Nope, still got all sorts of baby things. It even gets worse than that, because within the last couple of years, what they've done is actually age progressed my fur kid, and now I'm getting ads for toddler clothes. Okay? So this doesn't exactly work if you want to personalize whatever message you have to people in clustering. Something to think about. Okay, so there are other types of techniques out there. One of these is statistical techniques. And within these, you have all sorts of different types of quantization. K-means is something that probably everybody's talked about or heard. How many people here have been to a statistics class in their life? A lot, yeah, okay. You may have hated it, but this is probably one of the first things they taught you in terms of what to do with the data and how to cluster them. It's a fairly simple technique. You take a bunch of data points, you say, a priori, 4 clusters, because I think there should be 4 clusters, okay? You put the cluster centers at various points, and you run the algorithm. It figures out what's nearest to that. You calculate distances. It adapts the distances, adapts the points, and just keeps on doing that until you get what essentially you turn from that into a set of clusters over here. Fairly powerful technique, easy to understand. People can explain this to their boss. People can understand it themselves. That's not a problem. Problems are, number one, is that it assumes that the errors are nicely distributed. First thing you learn in your statistics class, and your professor will probably say, I'm going to assume that the world is Gaussian and all noise is round and it fits in this nice round ball. Well, that's nice for school, but doesn't work all of it in real world situations. Okay? So what happens if you don't have that? You get clusters that overlap, that don't really fit the data. These are also very well suited for small dimensional data. So if you have data that happens to be in the neighborhood of maybe a handful of different of parameters, fine. You can use these techniques, but they don't scale very well to larger dimensional spaces. And that's really what we're here for in the Hadoop environment, because think about it, I mean, we've got large data, we're processing a large number of different rows and columns at the time, huge dimensional spaces. These techniques do not really work well for those particular things. Now, one thing you can do, perhaps, is you can use different techniques to reduce the dimensionality, and then use these types of clustering techniques. Sometimes it works, sometimes it doesn't, but keep that in mind whenever you happen to use, again, k-means or some of the other vector quantization techniques. And there are a lot of them out there. Okay. So another possibility, feature maps. I don't know if anybody's seen these feature maps before. A guy named Teuvo Kohonen came up with this stuff back in, oh my goodness, I think it was like the early 80s or so. Very bright guy in Finland. And essentially what you're seeing here is a way to let higher dimensional data be projected onto a lower dimensional space. And you're not making the assumptions about how many clusters are there, because there aren't clusters. It's up to you to decide what those clusters are. So what essentially you're looking at is a heat map, okay? And if you let the data actually, and this is like a rectangular grid, you can use other types of grids. If you wanted to, you could use a sphere. You can map everything around a sphere. These things happen to have, the edges and the boundaries are close to that other side over there. You can use a torus. You can use all sorts of different shapes. It's up to you to fit whatever you'd like to have. But again, they're heat maps. And what they're showing is associations in space. So the things that are over here, all of these things in the green are proximal, and they have similar characteristics. Things in the blue have similar characteristics. So one of the keys here is then you can maybe think about this as like a topography map, and raise and lower the threshold on your topography. So add water to it. Anything below the level is in one cluster, anything above the level is another cluster. And you can have all different types of clusters over here. Very powerful technique. A couple problems with this also is that it's very slow to train, and also it's up to you to figure out what to do with that in terms of raising the threshold or lowering the threshold. A lot of times you don't have to worry about that because you only have so many different marketing campaigns or other types of things to do, so you can actually raise it on the fly and do that. One of the things that, at least for me, is very interesting is that it's not so much the clusters that are of importance, but it's actually what's on the boundaries of the clusters. What separates the things that are in the green from the things that are in the blue, or from the orange from the things that are in the yellow from the things that are in the green. If you want to think about this again in terms of a business, those might be people that are swing votes. Those are things that might be able to change. If you change their behavior or change your product offering or change whatever you're doing, your message to them, you might be able to sway them from one way to another. And if you can sway them, you might be able to get a sale out of that. You might be able to actually get something of worth from that particular information. So that's a powerful technique. Again, it's slow to train, but there are ways to parallelize that, and Hadoop actually allows that in terms of the Yarn environment as well. Okay. All right, so now we come to paralysis by analysis. You have a lot of different techniques out there. It doesn't matter whether it's supervised learning, unsupervised learning, it really doesn't make any difference. One of the first things you do probably, though, is you have to figure out what types of things you have in terms of your data. If you do have known truth or trustworthy truth, you can correlate that, and at least you can pick the model type that you want to use. If you don't have that, I definitely suggest types of models and just basic clustering things that don't rely on that type of truth. Okay? So, which one of these are you going to use for your problem? You need to solve it. Doesn't matter what it is, you need to solve it. Okay? What are the parameters that you need to use? How many different parameters are you going to set? Do you actually need to set those parameters, or you can actually use whatever you used last time because it seemed to work well? Okay? Two of the keys are, is this the best thing you can do? Should I have used a different model? What kinds, we talked about a few different models out there, quite a few other ones I haven't talked about, all different variants of these types of models. So, can you do better? How can you do better? What can you use to do better? All right, so that comes up to optimization. Maybe you can optimize this out. If you can automate this process and optimize the choice of model, that'll make your life a lot easier. Okay, so one of the first things as you think about is standard techniques to optimize. Again, you go back to math and statistics and all different things like that. One of the standard ways that they've been doing for a lot of years, again, Gauss and Newton came up with this back in the 1850s, they assume the world is a bowl. And that's a nice way because guess what? The math is very, very easy. If you have a world as a bowl, I'm going to assume that you have one optimum point. Okay, your solution is maybe at the bottom of the bowl. If you want to think about it the other way, turn the bowl upside down and the optimum's at the top. That doesn't make any difference. Just add a negative sign. There's no big deal there. Okay, and the math is easy to solve. The problem with that approach, though, is that reality hits, and reality is a bitch. In actuality, this is what the world looks like. Lots of minima, lots of maxima. It just doesn't fit this nice little bowl approach. The techniques that solve for optimization on a bowl basically walk downhill. Again, invert the problem, throw a negative sign if you don't want the downhill, you want to go uphill, that's fine. But if you go downhill and you hit one of these little local pockets over here and you don't have a way to go uphill, that's a problem. You're stuck in that. And all of a sudden you get a suboptimal solution for your problem, okay? That's not a good thing. And actually, what happens is that you'll end up with the wrong answer to the right problem, or the right answer to the wrong problem, okay? So, how do you come out of this, and what do you do in terms of a solution to this particular problem? Well, luckily, there are other ways to do this, okay? Again, I'm going to go back to statistics class in that most of the people thought that all processes have noise on them, and because they have noise on them, they're bad processes. Well, I'm going to come up with a different take on this, and that noise is actually your friend. It can be useful to you. Okay, so one of the things that's actually a very powerful technique is simulated evolution. And this is a way to optimize different problem spaces in a very efficient manner. Evolution has been around for a long time. Biology has been using natural selection and evolution for billions of years to evolve. Again, everybody who's sitting here is a product of it. It does a darn well job at optimizing in a dynamic environment. Okay, there's some failures. I admit the platypus, that was a mistake. But for the most part, it does a very, very good job. Okay? And it comes up with not just one solution, but a population of solutions. And the good part about this is that you can actually look at not just the best solution, but you can look at the second best one and see what's different from the third best one. And then maybe review whatever criteria that you have to assess which one of these is better for you and which one is not better for you. The process is very simple. Again, you start out with whatever hints that you have on the solution after you represent it in some way, your choice. This gives you a population of things that do. Variation and selection, basics of evolution. You vary the solutions in some way, you change some parameters, you change maybe in a modeling thing, how many different models you want to put in there, what are the parameters on the models, what are you doing with the models, types of models, all those different things like that could be in varied. You have to evaluate them. Which models did better than any other models? Okay, you take the best of those, you select those, and then you start the process over and over again. You just basically continue this until you come up with a solution that fits your criteria or fits your timing. You might just say, hey, I've only got 3 minutes to come up with this. Give me the best thing you got. The nice thing about this is that you always have a working solution. You never have to start from scratch because start with an existing solution. Okay, so what does a solution look like? I've been talking about this in terms of a model, but you can also use this in other types of processes as well. Anything that you can represent essentially can be used in an evolutionary optimization or stochastic method of this. Okay? So in a modeling type environment, we have, say, supervised learning. What types of supervised learning models do you want in the mix? You want maybe to throw a linear model in there, several different linear models, maybe a few neural network types. Throw them all in the soup. Let evolution figure out which of those are better than others for whatever you have. Let it vary the parameters on those. Let it vary the number of nodes in an artificial network. Let it vary the number of clusters that you have. Let it figure out whatever is doing best for your particular problem space. Again, and afterwards you do the training and testing on a particular problem. Okay, so what happens in a Hadoop environment? Now, the biggest problems here are to solve how do you partition this space? Because essentially what you've got is a lot of data, a lot of ways to get at the data very efficiently, but you also have to partition the problem. And these iterative problems have a couple different challenges with them. One of the ones is distributing the computation itself. Now, Yarn provides a nice framework for that, and it's very efficient at doing that. In some ways it's better, in some ways it's worse, in some ways it just does not work for some of these particular problems. One of the biggest costs along all of these is communication. Think about these as an iterative problem. When you have this feedback cycle, you need to somehow feedback how well you did to the other solutions so that they can be culled from the population. That communication takes time. And you have to consider that time in terms of what your overall process is, in terms of whatever algorithms that you can use on this. MapReduce, again, if you want to program that, there are different ways you can do that. Yarn actually provides a nicer framework on that. In terms of algorithmic partitioning, it's very good. It doesn't seem to be extremely well suited for these types of back and forth communication tasks with respect to the algorithms that are iterative, okay? Certain things that you can break down if you're searching for certain things, you might be able to combine them in one step at the very end, but if you need to feed that cycle back and have these iterative algorithms learn something, sometimes it can be a challenge in terms of the timing there. So what it comes down to is distributing them, aggregating the results, distributing them back out, aggregating the results as well. And again, the synchronization costs can get there. So I stole this from some cohorts over in Palo Alto at Stanford. This is one of the paradigms that they had come up with a few years ago. And it actually worked pretty well in terms of some of the different algorithms that they used on it. They used k-means algorithms. They used some linear clustering algorithms. They tested it with even actually a couple different neural networks and linear feedback models. And what's going on here is, again, you pick your whatever algorithm you want. It's typically a singleton algorithm. It's not partitioned per se. You let whatever engine that you have connect to a master controller that distributes whatever process that you want and split up the data, and then come back and use that algorithm to process that particular data. And the reducer reduces the different parts of this. It is somewhat communication heavy, and for some of these tasks, like for example, a k-means clustering algorithm, it works fairly efficiently. Some of the other algorithms that they tested on this, again, some PCA, some principal component analysis algorithms that seem to be working pretty well. Support vector machines, learning vector quantization types of things. Actually, again, I mentioned that the neural networks, the performance wasn't quite as good on that because there was a feedback of all of the errors on every single layer into the network that took time, and that actually slowed down the overall process. It was better than a straight one processor, one task at a time, but it wasn't really getting the linear gains that we were hoping for. So again, if you take a look, this is again one of their multi-core tests on a set of processors. And again, this is just a single example. There are a lot of different results out there. If you want to look up the literature, I can give to you. Let me know. But it does show a fairly nice, somewhat linear speed up in terms of the number of processors and the speed increase that you get out of using those processors for those types of singleton tests. So here's another architecture that you can use as well. This is machine learning on an evolutionary scale where you have a map reducer. Again, this is just another thing where you can actually have each individual offspring in a dynamic environment. Again, this is a simulated evolution type of a mechanism. And you map those down into smaller things. You can actually then produce results on each one of them separately, almost like a different island of populations type approach. And then you have one reducer, and then it's at the end after it does a lot of aggregation. And you take the best of those generations and you feed it back into the master controller. All right, so that's just another approach that you can use. All right, so again, the basics of whatever, and again, this is my take on this, basics of this machine learning is, again, take a look at what you have in terms of algorithmic bottlenecks, what algorithms that you can use on which environments, and that's a big key. If you have a large number of features with not too many intercommunication steps that have to feed back that information back and forth, Hadoop and MapReduce actually work very well. Otherwise, I would personally suggest using Yarn straight in, or potentially using a graphics processor unit to actually do the same tasking that you have. Adaptation. Last takebacks from this talk. Adapt, continually adapt. Make sure that you don't stay static. Change whatever you're doing. Do not just let your model be used for years and years and years. Change the time scales on your model. Take a look what's going on at maybe a daily model, a weekly model, a monthly model. Maybe use those all in parallel to solve whatever problem that you have. The timescale approach is very important. You can actually use a nested cascade of models all into the same output if you want to, okay? And the final thing is if you can automate this process. Again, the problem that I mentioned where it came up with models in a regression sense and they came up with nice plots on this, well, that doesn't always solve the problem, especially if you want to use this. If you can automate this, then maybe then you can take the human construct out of that and do a little bit better overall.
So unfortunately, that's all we have time for.
Okay.
We have 2 minutes before the start of the next.
All right. So again, I'll be in the lobby. We have a thing. Come to our booth, and I'll talk some more. Any questions you have.